let's look at some really basic concepts. So first, we're talking about isotopes. So this is an important term in radioactivity. And isotopes have the same number of neutrons, but a different number of protons. And the example on the left-hand side is the isotopes of hydrogen, where you have a different number of protons in the hydrogen molecule. The isotopes of each element can either be radioactive or not radioactive. And what that really depends on is the ratio between the neutrons and the protons. Another important term when we're talking about radioactivity, which comes up, is the term isomer. And an isomer is an element or different forms of an element where they have exactly the same number of protons and neutrons. However, they differ in the fact that they have different nucleus energies and different half-lives. And if you're not sure what those terms mean, we'll be discussing those later as well. But this is a concept that we need to be familiar with. So as I was mentioning earlier, when we're talking about radioactivity, we're really talking about what's going on in the nucleus. And we remember from the topics we looked at in matter and radiation that in the nucleus, we've got neutrons and protons. And it's the ratio between the number of neutrons and protons in the nucleus which determine the radioactivity of an element. So we've got an important graph on the left-hand side over here. So what we have on the y-axis is the number of neutrons, and what we have on the x-axis is the number of protons. And we're seeing that depending on whether the isotope has more neutrons or more protons, they are going to be either radioactive or non-radioactive. And if they are radioactive, they're going to be radioactive in different ways. So the nuclei of most atoms are stable, but if they are unstable, then we call them radioactive, and they're also called radionuclides or radioisotopes. So I find this graph on the left-hand side to be really useful because it's like a visual depiction of what kind of decay is going to happen if the number of neutrons is more versus whether the number of protons is more. And that is a question that could be asked in the part 1 exam. So what we're seeing in the graph on the left is that if the number of neutrons and protons is fairly equal, then that's those black blocks over there, then they're stable. Whereas if the number of neutrons is higher, then they will probably undergo beta minus decay. Whereas if the number of protons is higher, they'll be positron emitters or they'll undergo electron capture. And we'll look into those in more detail later as well. So there's around 2,700 known radionuclides, and most of them are artificially produced, and the ones that are used in medical imaging. So when we're talking about production of radionuclides, there's a few processes that we're looking at. So the first is in a nuclear reactor. Different types of nuclei are bombarded with neutrons in order to produce a new nuclide which has an excess of neutrons. And there's a reaction example which is given over there. And what's happening here in the nuclear reactor is that you're producing a radionuclide which has the same which has the same atomic number as the other non-radioactive elements in there. So what happens is they can't be separated from the original thing that you started out from. So that's one type of production of radionuclide. Another type is the production which happens in a cyclotron. So what's happening here in the cyclotron is that an element is being bombarded with positive particles, and then what's happening is that you're creating a neutron deficit in the radionuclide which is produced. And you can see that's what's happening in the reaction over here. So you've got an oxygen nucleus with 18 as the atomic mass number, and it's being bombarded with positive particles, and it's being converted to fluoride with the same atomic mass number because the proton has been absorbed and a neutron has been thrown out of the nucleus. And the characteristics of the radionuclides which are produced in this way is that they can be separated from the original carrier. This is because it's a new element that's being formed because the atomic number is changing, and they also have a pretty short half-life. So since the term half-life is coming up pretty often, I'll just give a brief description of it now. So half-life just basically describes how long, okay, I'll just give the full definition. So how long the activity takes to half, the activity of the isotope takes to half is known as the half-life. It's a description of how much radioactive decay is happening among the isotopes. We'll do like a proper definition of these later, but essentially the half-life is a measure of how much radioactive decay is happening. All right. So another type of production process which happens is in nuclear reactors. There's daughter products which are formed, which are also radioactive and which are useful. So what's happening is in the nuclear reactor, the fuel rods may be made of uranium-238, which is decaying to molybdenum-99, which is a very useful radionuclide. So it's a fission product from the reactor, which can be chemically separated and used. So another type of production process. Another kind of production process is using a generator. So in these generators, what happens is you have a parent nuclide, which then decays to a daughter nuclide, which is useful for us. So the example here is molybdenum atomic number 99, decaying to the metastable isomer of technetium with atomic mass of 99. Yeah. So what happens in these generators is that you have a long-lived parent, usually, and then what it gives rise to is a short-lived metastable isotope daughter nuclide. And what we mean when we say metastable is that usually when an isotope undergoes radioactive decay, the daughter nuclide which is formed is in its ground energetic state. That means it doesn't have a lot of energy. But in some, and this is because this is a natural thing in nature, it's the same reason why water doesn't stay at a height but chooses to come down. It's because they prefer to be in the ground lower energy state. But there's an interesting phenomenon which happens in radioactivity, which is where we have nuclei which exist in metastable states, which just means that they're able to exist in an excited state for a relatively long time. And a really famous and useful example of this is the technetium-99 metastable isomer. Okay, so that's a few important processes which are used to produce radionuclides. And this is an example of what some of this equipment might look like. So this I've taken from General Electric, and it's these small mini cyclotrons which can be used in the hospital itself in order to produce radio tracers that can be used for examinations. Okay, so now what we've done is just discussed a little bit about what is a radionuclide, why are some nuclei radioactive. So let's go a little further into what happens when a nuclide is radioactive. So what's happening here is that if the ratio of neutrons and protons is unbalanced, you have what's known as an unstable nucleus. And then this unstable nucleus is going to emit things in order to decay to a more stable state. So if it has more neutrons, it's going to emit particles which reduce the number of neutrons. If it has too many protons, it's going to emit particles so that the number of protons is reduced. And if it's just too heavy in general, then it's going to throw out particles so that the nucleus can become lighter, like what happens with uranium-238. And so the things which it throws out of itself in order to become stable are alpha, beta, and gamma radiation. And we'll discuss all of these in detail now. So one really important type of emission is the emission of beta particles. And a beta particle is actually a particle that we're super familiar with. It's just an electron. So it's a particle, a very light particle with a negative charge. And so I'll come to the graph on the left in a second. But what the nucleus achieves by emitting a beta particle is that it's used to convert a nucleus into a neutron into a proton. And the way that it's used is that we remember that the fundamental laws of physics are the conservation of mass and the conservation of charge. So what we need to remember here is the neutron is a particle with zero charge, whereas an electron has a negative charge and a proton has positive charge. So the nucleus wants to get rid of a neutron. And in order to do that, it has to change, and it wants to get a proton instead, but it can't go straight from zero charge to positive charge, from 0 to +1. So what it does is it splits into a +1 and a -1, so that when those are added together, it's still 0. So that's the use of the way the nucleus uses the beta particle. Another thing that it does is that it carries away energy from the unstable nucleus. So the nucleus does not want to have a lot of energy, and one way in which it gets rid of this energy is by throwing out a beta particle, which carries some of the energy away from it. So when we're talking about the particles and radiation which are used in imaging, one thing we're always interested in is the energy, because the energy determines the dose which the patient receives, as well as will the radiation pass through the patient, will it be picked up by the detector, because this is how the image is formed. So on the left-hand side is a graph of the beta particles' energy, the energy distribution. So on the y, or the vertical axis, is the number of beta particles, and on the x-axis, or the horizontal axis, is the energy of the beta particles. So if a radioactive element is emitting beta particles, what we see is it'll emit a lot of particles with certain different types of energies. So the important things we need to know about this graph is that there's a maximum energy, and I'll tell you why there's a whole range of different energies instead of being just one energy. So the energy, the transition energy, which the nucleus is getting rid of by transitioning to a different nuclide, is carried away by a beta particle and by a neutrino. A neutrino is a little particle which is going to take some of the energy, split it up with the beta particle. So imagine the total transition energy is 8, just a number. The beta particle might carry an energy of 5, and the neutrino will carry an energy of 3. So depending on how this energy is split up between the two particles, the graph on the left is formed. So if the neutrino gets none of the energy and the beta particle gets all of the energy, then that's how we get the maximum energy, which is equal to the transition energy. And that's the point, the rightmost point on the graph, the highest energy. And this is characteristic of every radionuclide. It can be used to identify the radionuclide. However, usually most beta particles don't have this much energy. They have a third of this energy. That's the average energy of a beta particle. So other things we're interested in is, once this beta particle is emitted inside the patient's body, what is it going to do in there? So it's going to follow a zigzag path because it's a charged particle. It's going to be interacting with the outermost electrons in the atoms in the patient's body and ionizing them. And when it finally runs out of energy in this pinball course that it's pursuing, it's come to the end of its range. And the range is inversely proportional to the initial energy, which makes sense. So if the initial energy is very high, the range will be less. And if the range is, yeah, you get it. And the range is usually a few millimeters. Okay, so that's a description of beta particles. Let's move on.